to the wire. 5 seconds. According to my watch. Okay. Let's shut the door and get started. It's all flash. All right, so today we're going to do a little review on Chapter 8, Chemical Composition. First, anybody have any specific problems we need to deal with before I start talking? Any review problems? Practice problems that gave you trouble? I'm just looking for problems from the peanut gallery. Okay, if there are none, we'll just jump into it, start working problems. Maybe something will occur to you. And if you think of something that's really bugging you, just stop me and we'll deal with it. All right. So let's just try the first one in this chapter. That one's not going to last very long. Not this one. That's better. This one is asking for the number of grams in 2.58 moles of sodium carbonate. So you're given 2.58 moles of sodium carbonate. And the question is, how many grams does that represent? Okay. What do we need to do first? This is where we are. This is what we've got. Yeah, the molar mass of the sodium carbonate you will need, right? But can we get it from that information? Not yet, because we don't know the formula for sodium carbonate. So we have to do that. So sodium is what? Na. Carbonate is C. You're on the right. CO3. Yeah, now that's in useful information. Right, take a look. Be sure and well, I handed one of these out. Right, practices. Right, so anything in the back, useful information will be on the test. You'll have that available. So the next thing to do is to correctly write this compound. Polyatomics always have a fixed charge. Right? For carbonate, the charge is 2 minus. Sodium has a fixed charge because of where it comes from. Okay. All those guys are +1. So now we just have to balance the charge. We need 2 of these to balance those 2. Okay, so now we have the compound written correctly. Okay, now we get to Josh's point. We need to know the molar mass. Why? Because if if this is where we're at, and this is where we're going, the conversion factor will have moles on the bottom and grams on the top. So the moles will cancel and leave you with grams. And remember, anytime you have grams and moles in a quotient situation, whether it's that way or that way, it doesn't matter. If they're in a quotient situation, think molar mass. So we just need to calculate the molar mass of sodium carbonate. So sodium is rounded off 23. Carbon is 12.01. And oxygen, we need 3 of them. That's 16. Right. Now, where did I get those numbers?
I don't know.
Well, I used to call them atomic weight. But these are average molar masses, or atomic masses. And I always round them off to 2 decimal places. That's good enough for our work. Okay, so now we need to find out what this value is. So that's 46, right? This is 12.01. And this is 3 times 16, 48. So that's 106.01 grams per mole. That's the molar mass of this compound. Right? And all you have to do is just add up the molar masses for each of the elements in the compound times however many there are. So that's what these are. 2 times that one, 1 times this one, 3 times that one. Add them up. Now we have our conversion factor for this compound. We know we have this many moles of it, and each mole weighs that much. So now we've done the thinking part. That's the hard part. The rest is just crunching numbers. You want to be sure you crunch the numbers correctly, of course. So you got to put them into your calculator correctly. 2.58, or your calculators, then divide sign, and then you say equal or enter, whatever the case may be. And I think I've made a mistake. No, divide. Did I say divide? Should have said multiply. Nobody corrected me. Okay, right? It would be divide only if that was on the bottom, but it's on the top. But the reality check, see, I did a reality check without saying anything. I looked at my answer and says, exponent of 10 to the minus 2. This does not compute, right? Because that's 2.5 times 100. How am I going to get a 10 to the minus 2 out of that calculation? So that's when I said, I did it wrong. 2.58 times 106. Now we get 2.74, we're limited to 3, times 10 squared. Grams. So that's how many grams we have, or 274 grams, which is the way it's written in the answers here for number 1. It's written in standard notation, so you would need to convert that to standard notation to find that answer in the multiple choice. Okay? Okay. That's some basic stuff. Let me check that one off so I don't come back and do it again. Let's do number 2. Take it baby steps. So we're given 8.52 grams of water. 8.52 grams of water. And the question is, how many molecules of water does that represent? The question is, molecules. Okay? So if we're given that, we need to go to this. What do we need first? Right, we need the formula for water. Right. There's your water. And we're going from mass to numbers. Right? And whenever you see going from mass to numbers or numbers to mass, you need to think molar mass again. Because that's what molar mass is doing. It's saying this many grams for that number, which is moles. That many grams for 1 mole, so your mass to numbers. You need to go from mass to numbers. So the first thing you've got to do is convert this to moles. Then we can convert it to molecules. So if we're going like this, and we're headed for molecules, we can get rid of grams and go to moles, but that's not molecules yet, right? We're going to need to go, once we get to numbers, we change this unit for numbers to that unit for numbers. So this is a chained conversion. We're chaining 2 conversion factors to get to our answer. So what's the molar mass of water first? 18.02. Because you've got 2 waters, 2 hydrogens, excuse me, and 1 oxygen. So that's 2.02 plus 16 is 18.02. So that goes here. That gets rid of grams, leaves us with moles. Now what's the conversion factor here? Going from, how many things are in a mole? That's really the question. This could be anything we want it to be. Yeah, you got that one already. There you go. That's how many things are in a mole. Let's see, did I put that in there? Or are you going to have to memorize that? Nope, got to know that one. Sorry. Just memorize it. 6.022 times 10 to the 23rd things is a mole of things. Doesn't matter what they are, whatever you need them to be. We need them to be molecules per mole. So now we got rid of moles and we're left with molecules. So that's the thinking part. Now you just crunch the numbers. 8.52 show up on our video too well there.
You lost me when you did the 6.02. Where you don't have anything, that's just what you
Whatever is equivalent to a mole, we need that many molecules in a mole to answer this question. If we were talking about atoms, if we needed to end up with atoms, and we already have the moles. We calculated moles. Then we use atoms per mole. This number is mutable. In other words, the number itself is constant, but the units of measure can change depending on what you need. Anything this many of something is a mole. Molecules in this case, atoms, ions, chickens, whatever it takes. So I get, let's see, I can keep 3 of them. 2.85 times 10 to the 23rd molecule. Let's see if that's one of our answers. Yep. So for number 2, the answer is A. All right, let's see. How many more? Okay. Let's do 3 because 3 is the converse of number 1. It's just a little more practice doing these conversions, and then we'll move on. How many moles of aluminum oxide? And they actually give you the formula, so you don't have to figure that part out. But since we're here, is this a type 1, type 2, or type 3 compound? Type 1. Because aluminum is always +3. If the metal is a fixed charge, that's a type 1. Okay, so let's move on. We're given 78.8 grams of that compound. And the question is, how many moles are there? Right, so we want to convert that one to moles. This time, grams on the bottom and moles are on the top. Still, it's a quotient. So grams and moles in a quotient means molar mass. So we just have to figure out what's the molar mass of aluminum oxide. Because we know we have this many grams, we want to know how many moles does that represent. So aluminum is what? Rounded off, 2698. Well, you were rounding too.
Yeah.
But let's not round.
Yeah, on here it said 26.98, so that's why I rounded.
Yeah. Let's not throw those decimals away just yet. And 3 oxygens. There we go. So now we can figure 2698 and then 48 for the oxygens. 101. Oops. 1.96 grams per mole. Okay. This means that grams is on the top, moles is on the bottom. But here we need grams on the bottom. Now, why can I do that? We have 2 answers. It's a conversion factor. But even more than that, I can flip it like that because all conversion factors are equal to 1. So it doesn't matter if it's this way or that way, it's still equal to 1. But I need it this way because grams on the bottom cancels grams on the top. It leaves me with moles on the top. So this one, I do need to divide. And 101.96. Now I get 7.73 times 10 to the minus 1. And then you look to see, is that one of the answers? Well, not exactly like that. So let's change it to standard notation. What would that be in standard notation? Minus 1? Which way is that decimal going to move? Should the number get...
It should go to the left.
Yeah, because the number needs to get smaller, right? That's a negative. It's got to get smaller, so it's got to move this way. Right?
So how did you get that number? The second.
I divided this one by that one. Right? Remember this one? Any number sitting out there by itself is always in the numerator.
Yeah, I did that. I think I did it because I've got the points instead of having 7.
It's the way your calculator's set up.
Yeah,
Because
that's why I was confused.
Your calculators are not set up to do to give you answers in scientific notation. It's okay in this case, but what if your answer were 7.73 times 10 to the minus 10? What would your calculator show you? 0, 0, 0, 0, 0, 0, till it ran out of room. It would not show the answer in standard notation because it would be 0.0000. In scientific notation, it will give you that part of the answer that you need. So my suggestion is go into your setup, change your output to scientific notation. It'll show, actually at your display, it'll show scientific notation for answers and for input after you put the number in. You can always punch the number in standard. Like you can punch this one in like that, that one in like that, and it will automatically convert it to scientific each time. Plus it'll give you your answer in scientific. Okay, so that one's A again. I'm trying to mess with your guessing technique here, right? Because when in doubt, what does it say? Guess C? On that page, if you guess C, you get them all wrong. I did mess up over that. I need to lighten my load here. Put that in. Oh, I got something for Victoria too. Here we go. All right, so that's very basic stuff. All right, number 4 is quite different than the rest of them, so let's just do it since we're in the neighborhood. All right, which of the following compounds has the greatest percent by mass of oxygen? Okay, so we're looking for, the question is, greatest percent. That's what that means, mass. Percent by mass of oxygen. So the first one is potassium carbonate. So they're giving you the names. What can we do with a name?
Break it into a formula,
You have to write a formula.
which will give you the number of oxygen, but won't give you the percentage, and that's the hard.
Right. So why do we even bother with names if we can't do anything with them? That's just the way the human mind works, right? Even when you see a compound written correctly, when you want to say it, well, you can say it two ways, right? Potassium carbonate. You can say potassium carbonate because you know that's how it's named, because you've practiced it enough. Or you can say K2CO3. Anyway, that's the first one. Second one is nitric acid. Right, so what do we need to have for an acid? At least one of them.
At least one hydrogen,
Lead with a hydrogen. And how about the nitric part?
you know, if I pick the right one.
That's right. -1 + 1. Now, well, I don't want to muddy the waters. That's right. Let's go to the next one. Zinc 2 oxide. Is that type 1, type 2, or type 3? Type 2. Because zinc comes from here
And the sheet metal.
in this region, right? So it's going to have the possibility for more than one charge. Now, if you look at your table, the periodic table, you find the zinc only has +2. Right? So in this class, you can use either method. Zinc 2 oxide would be that, because oxygen's 2-, zinc is 2+. We're saying it's 2+ here, but if you know your periodic table, you know that zinc is always 2+. So you could just say zinc oxide. And that's what you'll see on your tube of butt cream. Maybe butt cream, it'll have zinc oxide in it. It'll just say zinc oxide. Actually, that's not a good example because all those commercial products, they use archaic names anyway. Right? They don't use the modern system. So sometimes you have to interpret. For instance, toothpaste. The way they get fluorine into your toothpaste to help fight cavities and build enamel, they put it in there as stannous fluoride. Well, stannous is the old way of saying tin. So if you look and find SN here, it could be +2 or +4. So stannous fluoride does have tin and it does have fluorine, but the stannous means it's 2+, and the fluorine is 1-. So this means it's SNF2. If it says stannic fluoride, that would be 4+. So when you look on product labels, you're more likely to see the old way. And it's more convenient that way because, well, they're just complying with government regulations, so who cares, right? And if they said 10,2 fluoride, nobody knew what they were talking about, except the chemist. Okay, so next one is sulfur dioxide. Type 1, 2, or 3. Right, because sulfur, oxygen, they're both nonmetals. They're always type 3s. So you just say how many there are. So sulfur dioxide. That's it. Right, we never say monosulfur for the first one, for the cation position. If you say sulfur, that means there's one. If there were two, we'd say disulfur. So sulfur dioxide is SO2, pure and simple. And then we have an E, don't we? Yeah, diphosphorus pentoxide. So there you go, another type 3. This one is diphosphorus. And what is penta?
Not 4.
5. 4 is tetra.
Oh, there you go.
Think of it, if you need a reference point, think of carbon tetrachloride. Everybody's heard of carbon tetrachloride, right? Maybe not everybody. It used to be dry cleaning agent, right? But the OSHA and the EPA found that it was pretty hazardous for the workers. It's not hazardous for most people because we're usually not exposed to much of it at a time. But for the dry cleaning workers, they got exposed to massive amounts of carbon tetrachloride because all you need is a tiny leak and your environment is just saturated with stuff. So carbon tetrachloride was causing health problems for workers. So OSHA and EPA says, all right, you got to get rid of this stuff. So the industry protested, of course, but they gradually transitioned to something that was less hazardous. It's still hazardous, the dry cleaning agents, but they're not as bad as carbon tetrachloride. Okay, now we've got these, and we need to find out percent by mass of oxygen, right? So here comes Henry Ford, right? We're going to set up an assembly line. So how do you calculate the percent by mass of any element if you know the compound? You need the molar mass of the whole compound. Then you need the contribution to that mass of the element you're interested in. So for each one of these, we need the molar mass of the entire compound on the bottom. And then each one is going to be multiplied by 100 to make percent. So potassium chloride, 2 potassiums, right? 39.10. So this would be, I'm just going to put it down here. Potassium would be 2 times 39.10 plus carbon, 12.01, plus 3 oxygens. Right? Everything has to go in the denominator. The entire formula goes in the denominator for each one of those. Then you take the part of this that belongs to the element you're interested in this case oxygen, and put it on top. So 3/16 goes on top. That's your oxygen part. This is the compound part, oxygen compound. Then you just do that calculation and you get your percentage. We do the same thing for each one of these. So this is hydrogen, nitrogen, and 3 oxygens, right? So the 3 oxygens goes back up here on top. That's just coincidence. There's nothing special about that and that. It's just because this one has 3 and that one has 3 also. Nothing special about that. Okay, zinc, 6538, and 1 oxygen. So that 1 oxygen goes on top also. Okay. Sulfur, 3207. There's only 1 of them, but there are 2 oxygens which go on top also. Okay. And the last one, phosphorus 3097. 2 of them. And then 5 oxygens. And the oxygens go on top as well. All 5 of them. Okay? There's your pattern. The one you're interested in, every one that you have, divided by everything in the compound, all the elements. That's the hard part. Now we just have to crunch numbers. So 48 on top, and then we're going to add 39.10 twice. Oops. Back up. Okay, that's 78.20. And 12.01 added to that. 48 added to that. So that puts, let's just do it this way, because I know what some of you are thinking. How did he go from there to there? Okay, so the bottom is going to be 138.21. Okay, top's going to be 48. So we just need that one. And I get 34.73% oxygen. So this one has 63.02 on the bottom. And 48 on the top again for the oxygen. So that's 76.2 places, 1.7%. Okay. This one is 65.38 and 16. And then divide that into 16. And I get 19. Oh, I forgot to do that again. Let's be consistent. 81.38 on the bottom. And then only 16 on the top. I left out the 100 times each one of these. Okay. So 81.38 and then 16. 1966. Okay. This one is 32.07. And 16 times 6 plus 16 is 32. So this is 64.07 on the bottom. And 32 on the top. $49.95. And the last one, 2 times 30.97 plus 5 times 16 is 141.94. And then on the top, 5 times 16 is 80. So I get 56.36. Okay. So now we can compare the values and answer the question. Which one has the most oxygen? Looks like this one, doesn't it? And that's the answer given in the key. A lot of work. That's why I like to use an assembly line. Set it up, You gotta get all these right. They're giving, are they giving to us? No, we had to write it. You have to write these. Then you set up, what's the formula for percent by mass? If you know the chemical formula, then you put everything on the bottom and the element you want on top. Times 100. You just do that over and over and over again. Set it up right once. Be sure you're setting up right. Then repeat it with the specifics for each one. Right? So the process is the same. The numbers will be different. Okay. Questions? Stop me anytime. Because this train don't stop till it gets to Nashville. Okay. Good start to a country song. Okay, this last one on that page, number 5. That looks like a good bonus question. In fact, I do have bonuses on this one. The first 2 exams, I didn't have bonuses because you have got to know everything in those chapters before you fall. So if you get anything wrong in those first 2 tests, you need to correct those. But from now on, I'll have bonuses in the exams because things are starting to loosen up. We're using what we already know, and the bonuses are just kind of a step beyond. But, you know, sometimes the way the human mind works, you might read one of those bonus questions and say, aha, I know how to do that. But one that's in the required section say, oh, you know, that kind of situation. So the bonuses are there kind of as a safety net too. So number 5 on this first page. Okay, compound X2Y. What does that mean? That means we don't know what they are. And in fact, it doesn't matter. Now there's no X up here. There's an XE. Is there a Y? I think there is a Y. So that Y is called yttrium. We used to use that in the lab as an internal standard. That's neither here nor there. X2Y is known to be 60% X by mass. This is 60% X mass. Okay? And then the question is, we want to calculate the percent Y in this compound. The question is percent Y in that compound. Now, at first reading, that looks like an impossible problem to solve. So what you do is you tackle it with what you know. What do we know here? Well, we know this one is 60% X. So what percent is Y?
40.
Right, 40%. Okay, we're making progress. 40% Y. All right. Now you run into the roadblock that when you're talking about percent, that's a dimensionless number. That's so many parts per 100, right? So, but that can work to your advantage because if it says parts per 100, say, and by mass, we just say, all right, so many grams per 100 grams, right? So let's say we have 100 grams of this sample. So that means we have 60 grams of X and 40 grams of Y if we have a 100 gram sample, right? Okay. So now we can say, if this is 60 grams of X, how many grams for each one of those X's? This is actually 60 grams for 2 X's, right? So 1x is 30 grams in that compound. Okay. And this represents 1, y. Right, so 30 grams of x, 30 grams per x, 40 grams per y. Then what if we have 2 of those x's over here? Now we have equals 60 grams of x. And here we have 40 grams, but now we got 2 of them. So that's 80 grams of y for that compound. So what's the percent y? Well, we've got 80 grams of y. And what's the total? 140, right? So 80 divided by 140 is 57. 57%. Why? And then you look at your answers and say, okay, oh, there it is. D. So that's kind of, that's something you see in the newspaper on Sunday. You know, brain teaser, right?
It's actually fun if you know what you're doing.
Yeah, right.
Like watching,
It's like more like a
like once you
puzzle.
catch one, it's like, oh, this is
Yeah.
kind of fun.
It's more like a puzzle than
The
an actual
puzzle.
problem.
Yeah, right. So much for that. Let's see if we can progress before we run out of time. 57%. All right, I'll throw you a bone. That one will not be in a required section of the test. If it's there, it'll be a bonus. Okay?
Well, the ones I'm more worried about was like number 4, because that just took so long. I mean, it made sense, but it's gonna take me a while to work through a problem like that. So hopefully I'll be able to.
Okay, so we don't need to spend time on these guys because we've done things like that already. So let's move on. Okay, number 13. Now we're into a different topic with number 13. And this is all coming from the review document, okay? Choose a pair of compounds with the same empirical formula. So we've got these different compounds that need to be compared. Okay, this one and this one. And this one and this one. And then this one. This one. One. This one. And the last one. Compared with this one. Okay, empirical formula. Let's go back to the definition. What is the empirical formula? It's the simplest whole number ratio of atoms in a compound. Okay. So if you have subscripts on your elements and you can divide through by a common denominator and get a smaller number, then that's not empirical. The answer would be empirical. Okay. So the first requirement is, in comparing these two, is do they have the same elements before and after? I mean, in the two, right? If If they don't have the same elements, then they can't possibly have the same empirical formula. But you can't have an extra element in your, it just doesn't work. So hydrogen, oxygen, good. Carbon, hydrogen, okay. Chromium, potassium, chromium, oxygen, okay. Sodium, hydrogen, carbon, oxygen, missing a hydrogen. So that was gone.
So,
Same with E, right? You got an extra element in there, so just throw those out and don't waste your time on them. Now we have to decide, can this one be reduced any further? No. You can only divide through by 1, right? You can't get a whole number any smaller than 1. This one you could divide through by 2, but its empirical formula would be that, right? So those are not equal. Right, so that can't be it. Divide through by 2, what do you get? CH, right? Divide through by 6, what do you get? CH. Simplest whole number ratio. That's your answer. How do I know that's the answer? Because none of the others say none of these, or one of these, or 2 of these. Right? So once you find the right one, you can stop. But let's look at this one anyway. This one can't be reduced any further because that's a 1. And this one can't be reduced any further because that's a 7. You can't divide anything into an even and an odd and get a whole number, right? Okay. What is this compound though? Right. 3 elements, 1 of them is oxygen. So there has to be a polyatomic. Polyatomic, polyatomic. This one is chromate. And since that's potassium, it can only have 1 charge, type 1 compound. So that's potassium chromate. Right, and you can tell what the charge is on chromate because you know this one's +1, so that one has to be 2 minus. Because that's 2 pluses, has to be balanced. How about this one? Well, that one's also plus. So this one has to be 2 minus. That one's dichromate, but they both have the same charge. Now, does this chapter have, what was that last chapter? Oxidation states. Is that last chapter? Or did we do oxidation states in this one?
I think we both talked about it in the last chapter, but I don't think it touched too much on it.
We didn't do that. Okay, so let's just focus on charge. Charge there, balance, balance. And these are going to be, of course, in that table of your polyatomics. Chromate, dichromate. We used to use this one to clean glassware. Chromate, potassium dichromate mixed in with a concentrated solution of sulfuric acid. You could soak your pipettes in it, you know, especially if you were doing biological work. That always builds crud up in your pipettes. Pure chemistry doesn't do that. Most pure chemistry. Organic chemistry, yeah. That's the messiest of all the chemists, is organics. You know, if you walk into a lab and it's just looks like a hurricane hit it, that's an organic chemist lab. I don't know how they get anything done in those places, but they do. Anyway, but we would use that to clean out glassware. The strong acid plus the chromate would just completely eat that stuff up and just flush it out until they told us we can't use it anymore because you can't flush it down the drain because of the chromium. Okay, so we had to find something else. All right, that's 13. Let's see. We've done those. Let's see. Ah, 22. That's a different topic. Okay, it says acetylene gas is 92.3% carbon and 7.7% hydrogen by mass. Okay, we'll give them that. And its molar mass is 26 grams per mole. What's the molecular formula? All right, so there are actually two questions embedded there. With the percent by mass, you can find the empirical formula. But you have to have the second part where it gives you the actual molar mass of the compound to find out what the molecular formula is. All right. So let's do this. 22. Acetylene gas. All right, so we have 92.3% carbon, 2.3%. That's carbon. And hydrogen is 7.7% hydrogen. And I should move those a little further apart because we're going to have to do some calculations out there. Let's put it down here. 7%. Okay, that should add up to 100. Because we know we only have these two in there, so their percentages should be the total. But like I said before, percent doesn't get us anywhere. You need mass before you can convert to moles. Why do I need to convert to moles? Because the formula we don't know what these things are. The formula is numbers of atoms in ratio. It has nothing to do with mass. It's numbers of atoms. So we've got to convert these to a ratio of atoms to one another, right? So let's just assume we have a 100-gram sample. That's fair. 92.3 grams of carbon and 7.7 grams of hydrogen. We still have the correct mass ratio. How do I know? Well, what's the total mass here? 100 grams, right? So the mass percent of hydrogen is 7.7 divided by 100, which is 7.7%, right? So I haven't lied. That's the truth. But now we need to convert two numbers of each one. Grams on the bottom, moles on the top. Molar mass is what you need. Okay, so if we do that calculation, we'll find out what the mole ratio. If I didn't emphasize this before, let me do it now. One interpretation is so many atoms of carbon per atoms of hydrogen in the molecule. Right? But it also means so many moles of carbon ratio to so many moles of hydrogen. That's just as valid because you're still talking about numbers. Individual numbers, mole numbers, same ratio. So that's why we can find moles here and ratio them and still interpret it correctly for the compound. So 92.3 divided by 12.01 is 7.69. That's moles of carbon. And 7.7 divided by 1.01 is 7.62. Hydrogen. Now, normally what I would say is divide through by the smallest number. Right, so that would be this one. And we can do that just to be consistent. So that's going to be 1. So 1 hydrogen is ratio to 1 carbon. It's close enough. Do the math. 7.62 into 7.69 is so close to 1, you might as well round it. So the ratio, the empirical ratio is 1 to 1. That is There's the empirical formula for acetylene, 1:1. Okay? So if this were the formula for our compound, what would its molar mass be? It'd be 12.01, right? And 1.01. 2, 0, 1 grams per mole. Okay? But suppose, well, we don't know that. We need, what's the ratio of the true formula to the empirical formula, the molecular formula to the empirical formula? The ratio would then be mass of this one to mass of that one. And we're given the mass of this one, aren't we? 26. So that one is 26 grams per mole. So just ratio this one to that one and you'll find out what that multiplier is. And you can do that in your head. That's 2. N equals 2. So now we know that since these are 1:1 empirical, the molecular is 2:2. 2 times 1 is 2. Always has been, always will be. New math notwithstanding. Fortunately, when I was in grade school, they were teaching real math. It wasn't until maybe 10 or 15 years after that that they started teaching new math, whatever that is. For all I know, it could be counting on your fingers. That's the way my son learned it. But he's different. He would even do multiplication on his fingers. Never learned his multiplier tables. He knows them now because he's done it his way so long that he automatically knows what the answers are. So he could say, if I say, what's 7 times 6? He'd say 42. Because he did it the old way, adding up. Like his fingers were an abacus. So he just came at it from a different angle. So that's how you find the molecular formula. From percent composition, you make the empirical formula, right? You got to find the mole-mole ratios of your elements. Then you take that empirical formula and find out what is I call it the empirical weight. What's the empirical weight? And then you have to be given the molar weight, molar mass for the actual compound. Then you ratio the two and find out what's the nearest whole number ratio of those two. Okay. Then that ratio will tell you what the multiplier is. Then you multiply it through your empirical compound, and that gives you the molecular formula. Let's see. I want to be sure I get to. I don't want to miss any topics. 32 is another example. We can come back to that one if we have time. An example of just what we did, only with oxygen added in there as part of the compound. Let's see. You notice number 42 is crossed out. I don't know how that one got in there. But by the time I discovered it, I had already created this handwritten document. And it's numbered by this one. So I wouldn't go back and rewrite this whole thing. So I just crossed that one out and went in and edited this one to cross out number 42 from this one too. If you're curious as to why that is. Let's see. Okay. Lots and lots of the same kind of stuff we've done already. 63 is another example. 63, okay, let's do 63. It kind of takes off of where we've come from, only this might give you some trouble because it doesn't actually tell you what the exact molar mass is. And here's what I mean by that. It gives you the empirical formula, NH2O. That's the empirical formula. Okay? Then it says the molar mass is somewhere between 55 and 65 grams per mole. Right? At first sight, that might sound like I can't solve this problem because it could be 55, it could be 65, it could be 57 and a half. You know, who knows? It could be 60. But here's how you solve it. Here's the logic behind it. You're going to have to ratio some number here to some number that you derive from that one, right? So the empirical weight is going to be nitrogen, hydrogen, and oxygen, right? Let's just add those together and find the empirical weight. And 2.02, 16 is 32.03. Okay? So, and we're looking for that multiplier. So if the multiplier is 1, let's say if N equals 1, what does the molar mass or molecular weight, what is the actual molecular weight going to be for that compound? 3203, right? Because we only multiply it by 1. 32.03. All right, does that fit this scenario? Nope, it's too low. It can't be 1. What if N equals 2? What would this be? 64.06. Does that fit? Yep, it fits. So N has to be 2. We know it can't be 3 because that would put it outside the range. So don't waste your time on a test. You found the answer. N equals 2. So that means N2H4O2 is the formula, which in this case is B. Okay? So when you see that problem, first thing you're gonna do is your hair stands on end and you panic, right? But then after things settle down, use a little logic. Okay? How do we solve the problem if we do know the value? Well, you ratio them, right? So you can go the other direction. Instead of ratioing, let's say we know that it's 1. Does that answer the question? No, that's wrong. Let's say if we were able to ratio N equals 2, yeah, that gives us a valid answer. So there you go. Just come at it from a different direction. That's called critical thinking. As far as I know, there's no definition for critical thinking. I've looked and looked and looked, searched for it. Nobody has an answer. Critical thinking is like this umbrella. It covers everything, but they're expecting us to teach it without a definition. All right. So in this class, our critical thinking is scientific method, predominantly scientific method. So we can teach that. But this is an example of saying, what do we know? Where am I headed? Can I get there? Well, yeah, in this case you can. You just have to You have to know what the definitions are. How would I get there if I had the information I wanted? Well, I sort of have the information, but not exactly. So you work at it from a different direction to answer the question. Okay, let's keep searching. Still okay on time. There's a lot of repetition in this one. I think what I wanted was to emphasize the point. If you're not bored stiff working chemistry problems, you're not doing enough of them. Okay, that's my motto. Bore yourself to tears working chemistry problems. That's the way, that's the pathway to chemistry. That looks like an extra credit. Come back to that. I don't think I give you that type of question. 83. I don't think I put that in the required section. I want to be sure we get in everything. 91's another possible. 94 takes a lot of work. I try not to give you those types of problems that require 30 minutes worth of effort just to get a couple of points. It kind of defeats the purpose. Okay, 116 is another example of molecular formula. Okay. I think we've hit all the high points. We can go back and pick up, let's pick up this, this screwy one, number 91. So look at the way I work it. Oh, yeah, that should take it. It does take algebra though. So 91. A compound is composed of element X and hydrogen. So it's like this, like that, but there's more information. Analysis shows that the compound is 80% X by mass. So it's 80% X by mass. It has 3 times as many hydrogen atoms. Have I done this one in class? Well, it's deja vu. Must be last semester. 3 times as many hydrogen atoms as X atoms. So it has 3 times as many. That would be a valid empirical formula. We can't say that that's a molecular formula because all it said was 3 times as many. So it could be 6 to 2 or 9 to 3. But we should be able to answer the question anyway. What is element X? X equals what? Okay. Let's see, what do we know? Well, we know this is 80%. So what percent is hydrogen? Right? 20%. I might figure a new way to work this problem. I got a way that I've done here, but you know, maybe I don't need to. What if, Okay, I see why I did it that way. Okay, and that's a good way to think about it. How would we determine the percent X in this compound if we knew what X was? Right? We'd ratio, right? We'd have the total on the bottom, and then we'd have whatever X was on the top. Right? The amount of X would be on the top, and the total would be on the bottom. Okay? So, what would that look like? Well, the mass of X is going to be, let's do it like it's an algebra problem. Let X equal the mass of, not just the mass, let X equal the molar mass of big X. Okay? If we do that, then all we have to do to find this percent is put the amount of X up here and then the total on the bottom, right? So the total on the bottom, if this is grams per mole, right? Then the total on the bottom is going to be that plus whatever this one is. And we know what that one is. Right? 3 times 1.01. Good so far? Okay. Times 100 is equal to the percent of X. Okay. There we have our, we have an equation in one unknown we can solve for the X. So what would it be? Well, I'm going to simplify things. I will go ahead and do it that way. If we divide both sides through by 100, that gets rid of this 100, right? Okay, just puts it over here. So that's equal to 0.80. So this expression is equal to 0.8. So if I keep X on this side, and then X times 3.03 times this one, X plus 3.03. Everybody see how I got that far? Okay. I'm going to lose anybody. So now we expand this one, 0.80x plus, what's 3.03 times 0.8? Is 2.424. Okay. So now we can take, now that we've got these expanded, we can take this X and put it back over here. So this X, see if it's that right. Yeah. So this would be X minus 0.8. X equals 2.424. Okay.
See, I would want to divide the X by itself.
Oh, you can't. Yeah, you can't do that.
Oh, okay, the plus. I got
Yeah,
that. Okay.
right.
That's what confused me.
Yeah. So this is a positive. That's a positive. This positive comes over here as a negative. And then this would be 0.2, right? X equals 2.424. And X equals 2.424 divided by 0.2.
So where did you get the 42?
This is 1. 1 minus 0.8 is 0.2x. And then now we can divide both sides like you wanted to before. So 0.2 into this is like 2 into 24, right? That same ratio. Multiply the top by 10, the bottom by 10. That's easier to calculate than than 0.2. So if it's 24 divided by 2, 0.2 is about 12.1. And like we said before, it's grams per mole, and 12.1 grams per mole is where on the table? Carbon. Like, if I haven't said it before, I'll say it again. If you can calculate the average molar mass of an element, then a pretty good chance you can find it up here, because the molar masses vary similarly to the atomic numbers, right? They get bigger from left to right and from top to bottom. So you can follow them along and find that 12 point, is that 01? 2 into, yeah, 12.1, close enough, because nothing else is even close to it. So we would say that that's probably carbon. So it took a little effort. You have to think about getting from here. Actually, you didn't even need this. Getting from here to there, because this is the expression for percent by mass calculation. From here to here means that you've got to have the mass of this one and the mass of that one. Okay, so this is the mass of that one, the little x. And that one is hydrogen. And then this one is the big X, again, because it's got to be 80% X. So the leap from here to here is the real test. From there, it's just solving the problem. Okay, that was 91. Let's see. Has anything crossed your mind that wasn't at the beginning, something we need to deal with? So I'm kind of running out of things to talk about. Oh, I did take this one. Let's see. '83 is another brain twister, it looks like. That one would take too long. That's not something that I put on the test. It's just to give you your brain practice. Let's go back to that. Where is it? The one for vinegar, I think it is. No, that's a gaseous compound. Vinegar is the liquid. You know, you can get 100% acetic acid. You can buy it from a supply house. It's called glacial acetic acid. 100%, it's a liquid. Very heavy. And acetic acid vinegar is a weak acid by our definition. We haven't done that yet. No, okay. Never mind.
Well, there was questions in one of the homework about whether an acid was strong or weak.
Oh,
And I
okay.
don't remember about it in the lessons at all. It was just one random question in the homework.
Okay. Yeah. So by definition, a weak acid is just one that dissociates a little bit of its hydrogen, not a lot. A strong acid is one that completely dissociates. Every hydrogen that's in the molecule, put it in water, it's dissolved in water now. It's available.
Okay. Yeah, it was with the Aquarius questions.
Okay.
That makes more sense. That's why it wasn't with any of the others.
So, but by that definition, that doesn't mean that weak acids can't be hazardous. Because all you need is enough hydrogen to do damage. So if you get a very concentrated weak acid like this glacial acetic, you can stick your hand in it and come back with a skeleton. It'll eat it up. But I don't know where I was going with that.
I wouldn't mind doing some more calculations about mass, the really simple ones, the ones we started out with, just to run in the simple.
Okay,
Because it seems to be reoccurring a lot, at least that basis, and I would like to have it down really well.
you mean from the formula or from,
Well,
give me an example. Do you have one? here?
yeah, number 12,
Okay,
just the really simple ones, that way,
okay,
if I make sure I have the simple concepts so I can apply to the harder ones.
sure, sure. I'd rather do that than try to think up new things to talk about. Number 12. Okay, what's the mass of 5.826 moles? Oh, and it gives you the compound here. You don't have to do it from the name. That's good. Calcium hydroxide. Hydroxide is a polyatomic ion, so it has to be in parentheses if you need more than one of them. And you would, because hydroxide is a -1, calcium is a 2+, so you need 2 of them. But to make that conversion, question was, what's the mass? Okay, so we need to go from here, canceling moles, going to grams. Because that's in the numerator, that's in the denominator. This is where we're headed. So now you just have to decide, what's my conversion factor? And if it's grams and moles in a quotient, you know it's going to be molar mass. So calcium is 40.08. Try that again. Okay. How many oxygens do we have? 2. And we have 2 hydrogens. There we go. Did I lose you? Okay. I look for visual cues. And 32 and 2.02. 7410 is what I get. So 74.10 there. Take that one times 5.826. And I get 4.32 times 10 squared. Or the answer might be in standard notation, which would be 432 grams. Okay, so here's an example of, if the exact answer that you get is not there, pick the best answer. Right, 431.7. Yeah, I rounded off. That's what happened. Actually, I shouldn't have. Right? Because you've got 4 places there. Right? So that should be the right answer. I threw away a significant figure. Okay. Okay, 10 more minutes, I think. You got some others?
I was wondering if we could do a question that would involve using the number 6.022 to the power of like 23, I think it was.
Okay.
I'd like to do one that had it in it. I know there was
16.
There we go.
Yep. That looks like a good candidate. Okay. Okay, calculate the number of molecules in 0.0000400 grams of gaseous oxygen. Okay. So if we're mass and we need to go to numbers, we're going to have to know the molar mass of oxygen. Right. So here's one where you have to know gaseous oxygen is diatomic.
Oh, I knew that one.
Oxygen, nitrogen, fluorine, chlorine, bromine, iodine, and hydrogen. They're all diatomic. So when it says that one, when it says the name, better put two of them. And my guess is that this problem has taken that into account, that the student might make a mistake and just put one oxygen. So the answer for that one probably is here as a choice, but it's the wrong one. So we need to go from grams to moles first. All right, so this would be 1, 2, 3, 4. Minus 4 grams. And this is going to get rid of grams and leaves us with moles. So that's 32, because we got two of them, 16 each. And now we need to convert moles to molecules. So here's where your Avogadro's number comes in. There we go. Now we've done now that the brain fuse is done, it's all just math from here in. So that's 4 exponent. Divide and 6.022. Oh, I get, yeah, I can keep 3 of them. 7.53 times 10 to the 18 molecules. O2. There it is, D. Now, if we had used 16 here, what would that number be? Be twice as big, wouldn't it? If you divide by a number that's half the size, that would be twice as number. So it would be like 14, 15. So it'd be 1.5 times 10 to the 19. That's E. So it is here. But if you get that answer and choose that one, it's wrong. And all due to that fact right there. That's really the chemistry that's in this problem, is that. The rest of it is math. So that's why I said at the very beginning, I hope I said, a lot of chemistry you can solve with if your math skills are right. You just have to know what values to put in there, and this is just conversion factors. Dimensional analysis gets you from this unit to that unit because these factors are each equal to 1. Okay, we got 5 more minutes. Need another one?
I want to complain.
Well, let's see. What do we got going here? About 24. the molar mass of ammonium phosphate. We want to know the molar mass. Is ammonium or phosphate anywhere on that periodic chart? Nope. They're both polyatomics. Ammonium is NH4 with a plus charge. Phosphate is PO4 with 3 minuses. Okay. So all we have to do is balance the charges. We need 3 of these to balance those 3, don't we? So that means we need a parenthesis. Now that you know the chemical formula, you can calculate the molar mass. You just need 3 nitrogens. You need 12 hydrogens, right? We need 1 phosphorus, 30.97. And we need 4 oxygens. And that's, add them all together, of course. So I get 149. And I get to keep both of those decimals because we have 2 decimals all the way up and down. Even if you multiply them out, you still get those 2 decimals. So I get to keep both of them. Let's see if the answer is there. Close. Closest one is 149.09. So that's the one we pick. Must be a rounding error somewhere. Let's see, 09 would be 0.03. I bet that's it. That would be 0.03 difference. So this calculation must have been done with 14 rather than 1401. That was critical thinking. Yeah, we're searching out the answer. Okay, we're good. So you got the weekend to get this stuff down pat.
Will there be a buffer, so a study, a review day, or is it going to be at the test on Tuesday?
Test on Tuesday.
Test on, got it. It's just on chapter 8?
Tuesday, just on chapter 8. Right, and then we'll have, then we're going into chapter 6 and 7 after that. So we'll have 2 days of lecture and 1 day of review. There's plenty of room for that. I built in the buffer.
Got it.
So we can spend all Tuesday taking the test and you're done. Shut this thing off. We don't need any more dead air than required.